Thank you. I was a junior lecturer teaching +2, and then I did my PhD later in the Institute of Science and shifted to the Olympiad activity. Okay, the title of my talk is Integer Equations, Integer Solutions actually. So let me begin with a small problem. Okay. Suppose you have a water tank, okay, from which you can draw any amount of water. And you have this is actually a standard problem, a 7-liter can and a 5-liter can, 3-liter can. So there are no other measures. So how can you get exactly 5 liters of water into one of these cans? I mean, into this can, because 3-liter can cannot hold 5 liters. So how do you get exactly 5 liters using these two cans? Of course, it is easy to much easier to answer the question, how do you get 4 liters? Yeah, you fill up the 7-liter can and transfer it to the 3-liter can, and you get you are left with 4 liters in the bigger can. Okay. So how do you get 5? So that's to say, you draw water from the tank and transfer from one can to another can every time, and somehow you have to get 5 liters. Of course, you need to do a few operations for this.
3 liters to get like twice in transfer to 7 liters.
You fill up the 3-liter can and transfer to the 7-liter can. Okay. Oh, 6 liters. Okay.
Then again, we'll take 3 liters, transfer to the 7 liters, then
Yeah.
1 liter is gone, so 2 liters remaining.
Exactly.
4 into 5 liters, then again 1.3 liters.
Exactly. So what you do is you fill up the 3-liter can as many times as possible to fill up the 7-liter can. Okay. So let me write the solution in the form of a tabular column. So you have the water tank, and you have the 7-liter can and 3-liter can. Okay. So you draw 3 liters from the water tank. So this will be 3 and this will be 0 to begin with. And then you transfer from 3-liter can to 7-liter can, you get 3, 0. And again, you transfer from you transfer 3 liters to this, you get 3, and 3 is already there. And transfer it to the 7-liter can, you get 0, 6. Then again, take 3 liters into that, and this is still 6. And then you try to fill up this so that this is full. Okay. This can take how many more liters? 1 liter. So this is 7 and this is 2. So the appearance of 2 is a kind of encouraging number. And so now you transfer, so since you may not want to waste water, so you put it back into the tank. Okay. So you have 0, 2. And then you transfer from this to this, you get 2, 0. And then again, you transfer from the water tank to the 3-liter can, and you see that the final step is going to be 5, 0. So a certain number of transfers will give this 5 liters. Okay. Now you see that if you look at the operations, it's a kind of unidirectional. Now you can say it's clockwise. You are always transferring from water tank to the 3-liter can, 3-liter can to the 7-liter can, and 7-liter can to the water tank. So it's one complete cycle. If you reverse the directions of the operations, can you still get 5 liters? Okay, before we answer that question, let's see how this problem leads to a certain kind of algebraic equation. Since you are filling up from the 3-liter can to the 7-liter can, I'm going to write this equation, 3x minus 7y equal to 5. 3 and 7 are the capacities of these cans. And since you are transferring from 3 to 7, I'm writing plus 3 here as the coefficient of x and minus 7 as the coefficient of 5. And we need 5 liters, so I'm writing 5 there as the constant term on the right side. Now, this is a single equation in 2 unknowns. Normally, to solve for 2 unknowns, we need 2 equations. But yes.
Just wondering, any particular reason it was a negative sign?
Yes, because you are transferring from 3 to 7.
I think this is not matter finally. Why it will be negative?
Okay.
And what do X and Y equals, sir?
That's what, I'm coming to that. So, it's a single equation in two unknowns. Normally to solve for two unknowns, we need two equations. But here, we are looking for positive integral solutions. We want x and y to be positive integers. So under this extra condition, can we at least guess a solution? Okay. So can you guess a solution here?
More than 3 or
More than 3 certainly. So can you guess is the simplest possible solution? 4 and 1. Okay. So we have solved this equation for positive integers in x and y. But actually you see that x is the number of times you are filling up the 3-liter can, and y is the number of times you are emptying or filling up the 7-liter can. If you look at this, so it is filled once, twice, thrice, and 4 times. And the 7-liter can is filled exactly once. So x and y are not any numbers. They are the numbers which represent the numbers of the times you fill up the 3-liter can and 7-liter can. So as I said, can we reverse the directions and still get a solution? Let's say from water tank you fill up the 7-liter can every time. From 7-liter can you fill up the 3-liter can every time. And every time this is filled up, you transfer it to the water tank. Okay? That means we are solving which equation now? We are solving equation 7x minus 3y equal to 5, because we have reversed the operations, directions. Now can you guess a solution for this?
2 and 3.
2, 3. So now if you draw a tabular column like this, you will see that you would be filling up the 7-liter can exactly 2 times, and the 3-liter can would be filled up 3 times. So let me quickly do that. So these are the directions. So 7, 0 to begin with, and then you have 4, 3. Then you transfer empty the 3-liter can into the water tank. So that becomes 4, 0. And then transfer from 7 to 3, it becomes 1, 3. Then you transfer to the tank, it becomes 1, 0. And then you transfer 1 to the 3-liter can, it becomes 0, 1. Then you fill up the 7-liter can. Then try to fill up the 3-liter can. It takes only 2 liters, and therefore you have left with 5 here. And of course, later on you can transfer that to water tank. So you see that the 7-liter can is filled exactly twice, and the 3-liter can is filled 3 times. Where is that? Did I miss something? Yeah. 1, 2. Here. This is 3, sorry. It's right. So again, we have solved this equation also for positive integers. Now let's forget this problem. Again, look at the solutions. So let's look at this. So for this, we found out 4 and 1 as a solution. So can you guess the next solution? Next positive integral solution. Yes? Yeah, 11 and 4. You see that it's 11 and 4. 11 times 3 is 33. 4 times 7 is 28. Difference is 5. Okay. You may have to guess one more solution and then look for the pattern.
18 and 7.
18 and 7, exactly. 18 times 3 is 54. 7 times 7 is 49. 54 minus 49 is 5. Now you see that there is a pattern for the X sequence. So what is the pattern for the X sequence? It's an arithmetic progression increasing by 7 at a time. First term is 4. And the Y sequence is also likely to be an arithmetic progression increasing by 3 at a time. But these common differences are simply the capacities of the containers. Okay? I could say the common difference for Y is the coefficient of X, and the common difference for X is the numerical value of the coefficient of the Y. You can ignore the negative sign. Therefore, next solution would be 25 and 10. So why would such a thing happen? Why this will be again a solution if I add 7 to X and 3 to Y. Because if I add 7 to X, it increases by a quantity of 21. And if I add 3 to Y, it also increases by a value of 21. And 21 minus 21 gets cancelled. So each time you increase X by 7, and each time you increase Y by correspondingly Y by 3, there is an addition of 21 here and the addition of 21 here also, but because of negative sign, they get cancelled. And so how many solutions, integer solutions, do you expect to this equation? Infinitely many. And we can look at the general term, the so-called nth term of this arithmetic progression. So what would that be? It will be 7n minus 3. All of you know that the coefficient of n will be the common difference. And you need to add a certain constant so that when you put n equal to 1, you get the first term. Of course, when you put n equal to 2, you get the second term and so on. And similarly, this will be 3n minus 2. The coefficient of n is again common difference. And you have to subtract 2 so that when you put n equal to 1, you get 1 here. Okay. So we have the general solution, x comma y equal to, I will write it as an ordered pair, 7n minus 3 and 3n minus 2, where of course we say, of course, we have to say what n is, what the parameter n is. N is a positive integer. So for n equal to 1, we get the first solution. For n equal to 2, we get the second solution, and so on. So we have found out an infinite class of positive integer solutions. But one can prove that these are only the solutions. I'm not going into the details. But you can also, if you want many integer solutions, you can change the letter n into the letter z, where z is the set of all integers. So even if you take n as a negative integer here, okay, that will satisfy this equation. So here we are finding many integer solutions. A similar thing happens here also when you change the directions. The first solution was 2 and 3. So what will be the next solution? It will be 5 and 10, 35 minus 30. And next solution will be 8 and 17 and so on. So again, both arithmetic progressions. You have 3n minus 1 and 7n minus 4 as the general solution, where n may be allowed to be a positive integer or any integer if you want all integer solutions. Okay. So whenever we are solving a single equation in two unknowns for integers or positive integers in particular, such an equation is given a special name. Does anyone remember the name? Has anyone come across the name? They're called, such equations are called Diophantine equations, named after the Greek mathematician Diophantus, who lived during the 2nd century AD. He was interested in solving such equations. Okay, let's come back to the problem now again. Suppose instead of a 7-liter can and a 3-liter can, we had 6-liter can and 4-liter can, and we still wanted to get 5 liters from that. What do you think the situation would be like now? We have instead of 7 and 3, we have a 6-liter can and a 4-liter can, and we want 5 liters. Sorry?
6x minus 4.
So, okay, so the equation that is going to be solved is 6x minus 4y is equal to 5 or 4x minus 6y is equal to 5, depending on the direction. So what do you think of this equation about having positive integer solutions?
It's not possible.
It's not, exactly, it's not possible because both are even numbers. Both are even numbers. If you look at these scans, since these are even numbers, whatever transfers you make at any time, you will be left with only even number of liters in either of the cans. Or if you look at this equation, 6x is an even integer, minus 4y is also an even integer if x and y are integers. Therefore, the difference will be an even integer, so it cannot be equal to 5. So, not all such equations are solvable when you are given an equation like this. So, under what conditions will such equations be solvable? So, the general equation would be something like, look something like ax plus by equal to c, where a, b, c are integers in general, and we will avoid zero integer, because either a equal to 0 or b equal to 0 or c equal to 0 will not be of interest. So let's assume that they're all non-zero. So under what conditions do you think this equation will be solvable? A and B are even numbers. No, when they are both even numbers and the right hand side is 5, it is not solvable. The question is, under what conditions will this be solvable?
Both of them are odd numbers or
If I could rewrite it as y is equal to something, for instance, then I can say that the numerator should be some integer multiple of the denominator.
Okay, but a simpler condition, a condition which just pertains to only A, B, and C. Both odd numbers. So do you mean to say that if I had one even number and one odd number, I cannot get 5? Suppose I had 6 and 1, one even number and one odd number, I can still get 5 directly. 6 minus 1.
at least one odd number.
At least one odd number. Suppose I had 6 and 4, I can get 2 liters.
Prime numbers?
No, well, see if I had 9 and 4, both are, none of them is a prime number, but still I can get 5 liters.
ABC or co-prime?
A, B, C or?
Yeah. ABC or co-prime?
Well, that's a sufficient condition. A and B being co-prime is a sufficient condition, but not necessary. Because if I had 6 and 4, I can still get something like 2 liters. So A and B are not co-prime here. So if you look at the equation closely, you will see that the GCD of A and B, you know what is meant by GCD? What is the GCD of A and B? Greatest common divisor. Sometimes it is also written as highest common factor of A and B. Normally we reserve the term HCF for polynomials, but it doesn't matter. So GCD of A and B must divide C. You know this symbol, vertical symbol. Vertical symbol stands for divisibility. So if I write like this, it means X divides Y. And if I write like this, X does not divide Y. Okay. So that's a necessary and sufficient condition. We were able to solve this equation in positive integers because GCD of 3 and 7, which is 1, divides 5. Okay. We are not able to solve this equation 6x minus 4y equal to 5 because GCD of A and B does not divide 5. So this condition is both necessary and sufficient. Okay. So this was actually known to Greek mathematicians as well as some Indian mathematicians of the, so for example, Aryabhatta knew this condition as well. Aryabhatta, I think, lived during the 7th century AD, and it is also known to Brahmagupta, who lived during the 12th century AD. So they not only knew the conditions, but they knew how to solve such equations. Since these coefficients are very small, we are able to guess the solution, at least the simplest solution, quickly. Suppose I had written here 13x minus 17y equal to 5. Even then, it's not difficult to guess the solution because these are all small numbers, 13 and 17. But instead, suppose I had 113 and 117, then the difficulty level increases because you're dealing with 3-digit numbers. You also see that 113 and 117 are still co-prime, and therefore their GCD is 1, and therefore that divides 5. So this must have a solution, an integer solution. So how does one get a solution, at least one solution to such an equation, and therefore generate infinitely many solutions? Of course, we use a very useful theorem in number theory, which says that if x and y are co-prime, if GCD of x and y is 1, then there always exist numbers, integers a and b, such that ax plus by is equal to 1. This is a very well-known theorem in number theory, and it's very useful. If x and y are co-prime, then we can always find integers a and b such that ax plus by equals 1. If x and y are both positive, obviously you should expect at least one of a and b to be negative, one positive and one negative. Both cannot be positive because right hand side is only 1. Both cannot be negative also because right hand side is positive. So you should expect either a positive and b negative, or a negative and b positive. For example, if x equals 7 and y equals 3, so what are the values that we can get for a and b so that this combination is 1? You can easily guess that you can take a equal to 1 and b equal to minus 2, because 7 minus 6 is 1. Or else suppose this is 13, say, then it's 2 and minus 1, something like that. So you can always find solutions. But these values a and b need not be unique, because you can always increase one of them by b and decrease other of them by a, and so on. So these values of a and b are also not unique. There is also a procedure to find out these values. For example, if you want to solve, say, 19x minus 90y equals 1, then we know that the GCD of 1990 is 1, because there is no common factor. 1 divides 1, therefore this must have solutions. Now, how do you know that what is the procedure to arrive at the statement that the GCD is 1? There is this Euclidean division algorithm, from which we conclude that the GCD is 1, this division process. So it's 19 times 4, 76. Is it okay? Yes, 14. 14 times 1 is 14. Then 5 times 2 is 10. 4. 4 times 1 is 4. 1. And then 4. See, the last divisor is the GCD of the two numbers. Now this GCD, this not only tells us that 1 is the GCD of these two numbers, but it also gives us a method to calculate x and y, for which this will have a solution, positive integers x and y. How do you do that? We proceed in the reverse order. So this 1 is 5 minus 4 into 1, because 4 times 1 is subtracted from 5. And again, the remainder 4 can be written as 14 minus 5 times 2. So each time the remainder is written as the dividend minus the divisor times the quotient. So this is 5 times. Of course, one has to be careful. So this 4 is written as 14 minus 5 times 2, which is times 1. Now we bring together the coefficients of 5 and 14. which will be 5 times 3 minus 14 times 1. Each time you can verify also. 5 times 3 is 15, 15 minus 14 is 1. Again, what was the last remainder? It was 14. 14 is actually 90 minus 4 times 19. So this is 5 times 3 minus 90 minus 4 times 19 times 1. So 1 we can ignore actually. Now this is 5 times 3. No, wait. We need, sorry, there is some. So 5 times 3 minus, what was the last remainder? 14. 14 is 90 minus, no.
Substitute for.
I have to substitute for 5. Okay. No, 5 is, I have to substitute for 5. So what is 5? 19 minus 14. Yes, 19 minus 14 times 1. Yes, thanks. Okay. Minus 14 times 1. So this is 19 times 3 minus 14 times 4. Okay, 57 minus 56. And finally, we substitute for 14. So 14 is 90 minus 4 times 14. So 90 minus 4 times 14 times 4. So this becomes 19. So it's become 19 times 4 times 4 plus 3. That's also 19 minus 90 times 4. So our 1 equals finally 19 times 19 again minus 90 times 4, which is true because 19 times 19 is 361 minus 90 times 4 is 360. So we see that x equal to 19 and y equal to 4 is a solution, and from this we can generate infinitely many solutions. So this algorithm, which gives us this gives not only the GCD, but it also allows us to solve this equation by working in the reverse order, okay? By each time expressing the remainder as dividend minus divisor times quotient. Okay, of course, you have to do it a little carefully. Okay. So next, of course, then if you have something like this, or say, suppose you wanted to solve 19x minus 90y equal to say 7. How will you solve? You can make use of the previous solution. For x equal to 19, y is equal to 4, the right hand side is 1. So if you want 7 as the solution, as the constant at the right side, you just multiply these two by 7. Then you will get the corresponding solution for 7. So you have 19 times 7 would be 133 minus 4 times 7 would be 28. So that would be a solution. You can generate again infinitely many solutions. So thus you can solve in general ax plus by is equal to c. If a and b are co-prime, you first solve ax plus by equal to 1 using this procedure. And then using this solution, you can generate the solution for c just by multiplying both the solutions for c. Okay. Now, well, of course, both the Indian mathematicians and the Greek mathematicians knew this procedure because this Euclid algorithm was well known by then. So the Indians named this procedure Kuttaka. They had the algorithm itself was named Kuttaka. Brahmagupta not only looked at first degree equations like this, but he also looked at second degree equations. Some of the very common second degree equation is x squared minus 2y squared equal to 1, which has square terms. If the square terms are not present, then perhaps the solution is much easier. Suppose we look at this definite equation of second degree, which has square terms, x squared and y squared. Now, can you guess one solution for this equation?
Yes? 1, 0.
No, well, positive integer solution. See, we are looking at positive integer solutions.
3 and 2.
3 and 2, yes. Now guessing the next solution will be a little more slightly difficult actually, but let me give a hint that the next solution has both the values between 10 and 20. Suppose I give the hint that the next pair of numbers are both between 10 and 20, what would be the, what would be the exact values? What I mean to say is that even the next second solution is not difficult to guess. After all, they are the smallest possible two-digit numbers between 10 and 20. 17 and 12, yes. Good. 17 squared is 289. 12 squared is 144 times 2. So I will give the third solution myself. They are also two-digit integers, but you have to go a little far away, further, okay? 19 and 70, because 99 squared is, it's 9801. 70 squared is 4,900 times 2, it is 9,800. So if you subtract, you get 1. So that's the third solution. Now, do you see any pattern here directly? Yes? Do you see any pattern here? It's difficult to see any pattern, but let me tell you one or two or three methods by which you can get successive solutions. I think there are several methods to get the successive solutions. Let me try to, let's try to explore a few of them, okay? If with the first two solutions known, you can generate the third solution as follows. Assume that these two solutions are known, because it's not difficult to get them. So Brahmagupta had this trick. Look at the x values, you will multiply the larger number by 6 and subtract the previous number. 17 times 6 is 102, minus 3 is 99. You use the same operation for this also. Between the two values of y, multiply the larger number by 6 and subtract the previous number. It's 72 minus 70, 72 minus 2, which is 70. Now to get the fourth solution, you look at these two solutions, second and third, multiply this by 6, because between these two this is larger, multiply this by 6 and subtract this. You get, of course, it's you will get 577, and do the same operation here. 420 minus 12, 408. So you see, this will be the next solution, 570. You can actually verify. So this is one way you can get the successive solutions. And you can prove that all these are proper solutions. Therefore, this equation also has infinitely many solutions in positive integers. That's one way. And another method is, you don't have to even worry about two solutions. Just you take one solution at any stage as, say, xk comma yk, and use these two together to get the next solution. The idea is to take a combination, 3xk plus 4yk as the next value of x. I will call it xk plus 1. And yk plus 1, the next value for y, will be 2xk plus 3yk. Look at this combination. Suppose 3 and 2 are known, so multiply the x value by 3 and y value by 4 and add. You get 9 plus 8, 17. That will be the next x value. And you multiply the x value by 2 and y value by 3 and then again add. 2 times 3 is 6, 3 times 2 is again 6, 6 plus 6 is 12. Again, from 17 and 12, you use the same pair of equations to get the next solution. 17 times 3 is 51, plus 4 times 12 is 48, 51 plus 48 is 99. 2 times 17 is 34, plus 3 times 12 is 36. Again, you get 34 plus 36 is 70. And you can proceed like this is another way. So this involves the use of only one solution being known to get the successive solutions. Okay. But perhaps better than these two, there's one more method. Okay. Now, if you look at the equation x squared minus 2y squared equal to 1, how would you factor the left-hand side? What would be the factors of the left-hand side? Yes, you would factor it as, in terms of irrational numbers, x plus root 2y times x minus root 2y. Now, here we'll just take one factor, x plus root 2y. Okay. And substitute the first solution. Of course, we need to know the first solution, x equal to 3 and y equal to 2. So it becomes 3 plus 2 root 2. See, then we need to know something about binomial theorem. I hope all of you know about the binomial theorem. So normally the expansion of a plus b whole to the power of n contains how many terms? N plus 1 terms. But suppose I take an expression such as 3 plus root 2 whole to the power of say 5 and try to expand and try to simplify, how many terms would it eventually contain? 2 terms only. Why only 2 terms? Because the powers of root 2 are either integer multiple of root 2 or an integer itself. Okay? Root 2 whole squared is 2, root 2 whole cubed is 2 root 2, root 2 whole to the power of 4 is 4, and so on. So these powers of root 2 are either integer multiples of root 2 or integers themselves. When you simplify this, you will get an integer plus root 2 times another integer. Well, let me write some other numbers, a1 and b1. Okay, now we are going to expand the nth power of this number and look at the right side. Okay? So if I expand this, you will get some integer, let me call it xn, then root 2 times yn. Well, let me give an example for here. So if you have 3 plus 2 root 2 and square it, the first term is the integer 3 squared. The 2ab term has root 2, and the second term will have root 2 whole squared, so that will be 8. So you can combine integers and have xn and come here, and the term containing root 2 will be there. Okay. Okay. So 3 plus 2. Let suppose that the nth power of this is xn plus root 2yn. What can we say about the nth power of 3 minus 2 root 2 whole power n? Xn minus root 2 by n, precisely, because only alternate terms which contain root 2, okay, will get the negative sign. The even powers of root 2 will have positive signs, and they will again add up to xn. All the terms containing root 2 will have negative signs, and they will add up to yn. So if 3 plus 2 root 2 whole to the power of n is xn plus root 2, it's something like taking conjugates. 3 minus 2 root 2 whole to the power of n will be this. Let's multiply these two equations. So if you multiply these two equations, what do you get? What is 3 plus 2 root 2 whole power n times 3 minus 2 root 2 whole power n? And that's equal to xn plus root 2 yn times xn minus root 2 yn. So what will be the left hand side? Yes, 3 plus 2 root 2 times 3 minus 2 root 2 is 3 squared minus 2 into 2 squared, which was a solution of this equation, which happens to be the left hand side here. So that has to be 1. 1 to the power of n is 1 again. And this multiplied would give us xn squared minus 2yn squared. So you see that xn and yn are a pair of solutions to this equation, because if you put x equal to xn and y equal to yn, you are getting 1. And what are these xn and yn? They are here. You just expand using binomial theorem this expression, 3 plus 2 root 2 whole to the power of n integer part, rational part is xn, kind of irrational part is yn, and those two are precisely the solutions for this equation. So, for example, if we take square, 3 plus 2 root 2 whole squared, which we did earlier, okay? What do you get? You get 9 plus 8, 17, plus 12 root 2. So 17, the real rational part, 12, and 12, the irrational part, are the solutions of this equation, which was written here. 3 plus 2 root 2 whole cubed. You are going to get 99 plus 70 root 2. Therefore, 99 and 70 will be the third solution, and so on. So for every nth power, you will get a solution. And you will have infinitely many solutions. So this is another way you can generate infinitely many solutions. In any case, finding the simplest solution may be somewhat easy for small numbers like 2 here, but if you have other numbers, it may turn out to be very difficult also. So, for example, Brahmagupta wanted at one time to solve this equation x squared minus 61 y squared equal to 1. I don't think it will be very easy to guess even the simplest solution. To make the right hand side as small as possible, perhaps we can take x equal to 8 and y equal to 1. If we take x equal to 8, y equal to 1, we'll get right hand side equal to 3, but we won't get 1. But he had an algorithm to generate the simplest solution. And using the simplest solution and this kind of argument, he could generate infinitely many solutions. The simplest solution itself had a large number of digits. For example, the simplest solution for x will have 10 digits, and the corresponding solution for y will have 9 digits. So it will run into billions. That would be the simplest solution. But he had an algorithm for that, and that algorithm was called Chakravala. So this was done by Brahmagupta of 12th century AD.
Can I interrupt?
Yes.
I'm wondering, Western culture and societies, you want to quote sources, they insist where we get this information from.
Sorry.
In Western, from the research in the Western culture, even in India, of course, when you cite somebody else's work, you need an authentic source.
Yes.
I'm wondering, where do we get...
Brahmagupta had written books on this.
Yeah, well,
Brahmasputa Siddhanta, something like that. So, but all those are written in Sanskrit, because Sanskrit, just like in the European countries, things were written in Latin until perhaps mid-19th century. Ancient Indian mathematicians, who were basically astronomers, they wrote these things in Sanskrit, that too in verse form, shloka form, not even in prose form. So, those Sanskrit texts are available even now.
What do universities have? Do universities, research institutes?
No, they will be available in, only perhaps the interested mathematicians of yore perhaps took interest in this and lot of interest in and did lot of research and brought out these things. English translations are also available. Okay. So, Chakravala. Some Jain mathematicians also were interested in this second degree equation, and they had a different name for the same algorithm. They called it Bhavana. So there are two names for this algorithm. The Jain mathematicians called it Bhavana, and Brahmagupta had this name, Chakravarti. So, suppose, not only x squared minus 2 y squared equal to 1, several such similar equations can be solved. For example, if d is a positive integer, x squared minus dy squared equal to 1 can be solved similarly, provided d satisfies a certain condition. For example, I can take d equal to 2 or 3, but I cannot take 4. I can take 5, 6, 7, 8 for d, but I cannot take 9. So what sort of numbers are prohibited? Square numbers. Yes. So if d is a square, there are no solutions, no positive integer solutions for such an equation. Of course, to prove that is very easy. Suppose you took d equal to 4. how do you prove that there are no solutions? You can now factorize this into rational parts, rational expressions. What would be the factorization? X plus 2y times x minus 2y equal to 1. X and y being positive integers, x plus 2y and x minus 2y also will be positive integers. Product of two positive integers is 1. Therefore, what is the only possibility? If product of two positive integers is 1, they have to be each 1. X plus 2y is 1 and x minus 2y is also 1. So we have two equations in two unknowns now, and we can solve for x and y. So what solutions will you get? X equal to 1 and y equal to 0. So 1 and 0 are the only solutions of this equation. So there are no positive integer solutions for this. Of course, if you can allow x, if I allow x to be negative also, x equal to plus or minus 1 and y equal to 0 will be a solution. Because even for this equation, we said 3 and 2 are solutions, but you can change the sign of x as well as y, okay, at your will, and still have a solution. Minus 3 plus 2 will be a solution. Minus 3 minus 2 will be a solution, and 3 minus 2 also will be a solution. You can change the sign of one of them or both of them. So for each such positive integer solution, in all you will have 4 positive integer solutions. And if you look at the geometrical aspect of this, what does x squared minus 2y squared equal to 1 represent in the xy plane? Hyperbola. So we see that this particular curve, which looks like this, will have, besides other points, it will have 3, 2 on its on one of the branches, and 3 minus 2 below. Here you will have minus 3, 2, and here you will have minus 3, minus 2. So corresponding to each positive integer solution, you will have 3 more solutions. Okay. So you see that if D is a square, there are no solutions. Besides 3, 2, we found out several other solutions. For example, 17, 12 will be a solution, 19 and 70 will be another solution, and so on. Sorry. And whenever the coordinates of a point are both integers, it has a special name again. Such points are called lattice points. If both coordinates are integers, we call such a point a lattice point. So what we have done is that we have proved that this equation, when represented as a hyperbola, will have infinitely many lattice points on that in the first quadrant, and therefore as many in the second quadrant and third quadrant and fourth quadrant. So all these are lattice points. Of course, there will be other points also. Perhaps they will have irrational coordinates, or one rational, the other irrational, and so on. But certainly it will have infinitely many lattice points, both of whose coordinates are integers. Well, this was done during the 12th century, but later it was also considered by European mathematicians, and until recently it was called Pell's equation. Although by mistake, Pell was not responsible for solving these equations, but it was by mistake called Pell's equation. But when the Europeans came to know that this also solved earlier by Brahmagupta, now they have started calling it Brahmagupta-Pell equation. Well, besides, you can take some negative integer values also on the right-hand side. For example, x squared minus 2y squared equal to minus 1 also, one can prove that has infinitely many solutions. The method is similar with a slight change. First, we guess the smallest possible solution. So what is the smallest possible solution for this? 1, 1. And with this, we construct 1 plus root 2 into 1, just like we constructed 3 plus 2 root 2. Since x is 1, y is 1, x plus root 2 y will be 1 plus root 2 into 1, which is simply 1 plus root 2. Okay. Into 1 minus root 2 is minus 1, if you factorize this. So if you raise both sides to even powers, you will get plus 1. But we want minus 1 here, therefore we raise both sides to odd powers. So just take 1 plus root 2 and raise it in odd power like 2n plus 1 and go on calculating the rational part and irrational part, you will get successive solutions. For example, if you take n equal to 0 here, I will take 2n minus 1. If you take n equal to 1, if you take n equal to 1, you get 1 and 1. If you take n equal to 2 here, it becomes 1 plus root 2 whole cubed. You can easily say that this is 7 plus 5 root 2. I mean, again, the entire sum will collapse to 2 terms. Okay? So 7 and 5. You see that 7 and 5 will be the next solution. 7 squared is 49 and the next term is 50. So 49 minus 50 is minus 1 and so on. So you will have to take odd powers here so that you get minus 1. And one can again prove that these are the only solutions, but that needs a little theory. On the other hand, while x squared minus 3y squared equal to plus 1 will have solutions, it's not difficult to prove that x squared minus 3y squared equal to minus 1 has no solutions. So just like in the first degree case, we saw that 6x minus 4y equal to 5 had no solutions. Similarly, not all such, even though this is not a square, you cannot take minus 1 here. The reason is that, so when do I stop? 5 minutes. What is the reason? The reason is that if you look at any general number n and say divided by 4, what are the possible remainders? 0, 1, 2, 3. So if the quotient is k, we can say that any positive integer of the form is of the form 4k plus 0, that's 4k, or 4k plus 1, or 4k plus 2, or 4k plus 3. But if you look at these squares and divide by any integer square and divide by 4, what are the possible remainders? 1, and then? If you divide 1 squared, you get remainder 1. If you divide 2 squared, you get remainder 0. If you divide 3 squared, remainder 1. 4 squared, 0. So alternately, we will get 0 and 1. So these are the only 2 remainders when squares are divided by 4. You don't get either 2 or 3 as remainders when a square number is divided by 4. Similarly, you can explore for other possible divisors. For example, if the divisor is 3, the possible remainders will be 0, 1, 2. Here, the remainders won't be all the 3 numbers 0, 1, 2. It will be a smaller set. We are interested in only in 4 here. So every square leaves a remainder either 0 or 1 when divided by 4. Because if it is even number, if n is even, square will be divisible by 4, therefore it leaves a remainder 0. If n is odd, you can write it as 2k plus 1 or 2k minus 1. And if you square it, you get 4k squared plus 4k plus 1. So 4k squared plus 4k is divisible by 4 and the 1 is the remainder. Okay. Now how is this useful here? So x and y are squares. They may be even or odd. So what are the possible remainders here? So this will be either 4k or 4k plus 1 x squared. This will be minus 3 times. What are the possible values of y squared? Either 4l, we have to take a different number here, or 4l plus 1. Now, so this is the nature of this, nature of the number x squared. This is the nature of the number y squared. But you are multiplying by minus 3 and subtracting. So there are all possible combinations. If you can take these two, these two, these two, and these two. There are 4 possible combinations. If both are divisible by 4, do you think x squared minus 3y squared will be equal to minus 1? X squared is of the form 4k. Y squared is also for the form 4l. Do you think the difference will be minus 1? No, because left hand side is divisible by 4. If x squared is 4k and y squared is 4l plus 1, and if you multiply by minus 3 here, it will become 4k minus 12l plus 3. Okay, can that be equal to minus 1? See, this is same as 4k minus 12l. If minus 3 go to the right hand side, it's equal to plus 2. So 4k minus 12l is 2. It's not possible because left hand side is divisible by 4, right hand side is not divisible by 4. It's just 2. Similarly, you can verify that the remaining combinations lead to impossible equations. Therefore, we conclude that x squared minus 3y squared equal to -1 has no solutions. So not all, but it's true that x squared minus dy squared equal to +1 will always have infinitely many solutions whenever d is not an integer. And lastly, I will just give one application of this. So where do we apply these things? If you look at Pythagorean triples, okay, what are Pythagorean triples? X squared plus y squared is equal to z squared, x, y, z are integers. They're called primitive if there are no common factors. If you look at some of the triples like 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, and so on, you see that in many cases there are many triples with y and z differing by 1, hypotenuse and one of the legs differing by 1. But there are very few triples with x and y differing by 1. Okay? 3, 4, 5 is 3 and 4 is one such instance. Do you know of any other Pythagorean triple where x and y differ by 1? Any primitive Pythagorean triple. Anyway, it will be primitive because they differ by 1. Those such triples are obtained by this equation. We saw that one solution is 1, 1, which is we'll ignore that. 7, 5 is the next solution. Next solution will be 41 and 29, because 41 squared is 841. 29 squared is, 41 squared is 1681, and the right hand side, the second term will be minus 1682. And the next one will be, again, multiply by 6 and subtract. It will be 233 and 169, and so on. Okay, let me finish in a minute. Look at the x values. You split them into two. So these are the infinitely many solutions of this equation. You split the x solution, x value, into two consecutive integers because they will be all odd numbers. So what do you get if you split 7 as the sum of two consecutive integers, 3 and 4? So they will form the legs of a primitive Pythagorean triple. If you split 41 into two consecutive integers, you get 20 and 21, and this 29 will be hypotenuse. So 20, 21, 29 is a primitive triple, okay, with the legs differing by 1. Similarly, if you split 233 into two consecutive integers, you get 121. Is it? No. This number is wrong. 6 times 239. So you get 119 and 120. 239 is 190. And the hypotenuse will be precisely 169, the y value. Okay? So you see that this equation has certain applications in finding primitive Pythagorean triples of certain nature with the legs differing by 1. So similarly, of course, later on, mathematicians have considered lots of such Diophantine equations, second degree, perhaps higher degree, and so on. And that's all part of number theory. Okay? Let me stop here.